The universe is expanding. You've heard it. But have you ever stopped to really think about what that means? Is it like a balloon inflating into empty space? Or a bomb exploding outwards? Our intuition screams, expanding into what? But what if the truth is far stranger, more profound, and defies everything your mind assumes about space and reality itself? If the universe is everything, how can it expand? If there's nothing outside it, what does expansion even signify? These aren't just casual questions. They go right to the heart of how we think about space, time, and reality itself. If you love exploring the universe's greatest mysteries, you're in the right place. Join the Stellify science community on our quest to unravel the cosmos. Subscribe and hit the notification bell so you never miss another adventure. In this video, we're going to pull this question apart piece by piece. We'll look at what scientists actually mean when they talk about expansion, how the evidence for it was discovered, why our brains struggle to make sense of it, and what it might tell us about the ultimate fate of the universe. By the end, you'll see why the question, expanding into what, is both misleading and surprisingly profound, and why the real answers are stranger than you might expect. For most of human history, the universe wasn't thought of as something that could expand at all. Space was seen as a fixed backdrop, the stage on which everything else played out. The stars moved, the planets wandered, but space itself was assumed to be rigid and unchanging. This static view of space was deeply rooted in the classical geometry that humans developed to understand their world, where distances and shapes remained constant. To get to the root of why expansion feels so counterintuitive, we have to go back to the foundations of geometry, the very rules we use to describe space in the first place. 2,000 years ago, a Greek mathematician named Euclid tried to write down those rules. His book, Elements, became one of the most influential works in history. In it, Euclid laid out the basic postulates of geometry, how points, lines, and shapes behave. Most of them are so obvious that you almost take them for granted. A straight line can be drawn between any 2 points. A circle can be drawn with any center and radius. Things like that. But then came the fifth postulate, the one that would cause trouble for centuries, the parallel postulate. In simple terms, Euclid's fifth postulate says that if you have a line and a point not on that line, there is only one line through the point that will never meet the first line, no matter how far you extend them. That's what we mean when we say parallel. It seems obvious. Parallel train tracks never meet. Two rulers held side by side don't cross. And for nearly 2 millennia, mathematicians tried to prove this postulate from the first 4 postulates, thinking it was too clumsy to be fundamental. They succeeded with these other postulates, but the parallel postulate always resisted. By the 19th century, something shocking became clear. The reason nobody could prove it was because it wasn't universally true. Mathematicians like Nikolai Lobachevsky, Janos Bolyai, and later Bernhard Riemann showed that you could construct entirely consistent geometries where parallel lines did meet, or where there could be infinitely many lines through a point that never intersected the original line. Geometry wasn't unique, it wasn't absolute. Suddenly, space could be curved, bent, and twisted in ways Euclid never imagined. Why does this matter for the universe? Because the geometry of space determines whether it has edges, how it curves, and whether expansion requires an outside. If space were exactly Euclidean, then it would be infinite and flat, stretching on forever in every direction, never looping back on itself. But if space is non-Euclidean, strange things can happen. Travel far enough in one direction, and you might loop back around like circumnavigating the Earth. Draw a triangle across curved space, and its angles might not add to 180 degrees. In other words, geometry opened the door to universes that didn't need an outside at all. To bring this down to Earth, think about the surface of a globe. If you start at the equator, head north to the pole, then turn and head back down, you can form a triangle with 3 right angles, 270 degrees in total. That would be impossible on flat paper, but it's perfectly fine on a sphere. This is non-Euclidean geometry in action, and it taught us something crucial. The rules of space depend on the space itself. They're not universal laws imposed from outside. For centuries, the debate over the parallel postulate might have seemed like pure mathematics, far removed from astronomy or cosmology. But when Einstein came along in the early 20th century, these ideas about curved space became the backbone of his general theory of relativity. Space wasn't a static backdrop anymore. It was dynamic, stretchable, bendable. Gravity itself wasn't a force pulling objects together, but the result of space curving around mass. And here's where the connection to our original question starts to appear. If space can curve, then it doesn't need to be embedded in some larger external arena to do so. Just like the surface of the Earth curves within itself, space can expand or bend without requiring an outside. Non-Euclidean geometry broke the spell of Euclid's 5th postulate, and in doing so, freed scientists to imagine universes that don't need a container. That was the first crack in the assumption that the universe must expand into something. But mathematical possibilities aren't enough on their own. To prove that the real universe expands, astronomers needed evidence. They needed to look through telescopes and actually measure where the space was stretching. And that's exactly what happened in the early 20th century when a Belgian priest, an American astronomer, and a few careful measurements of starlight would change our understanding of the cosmos forever. The idea that the universe itself could expand wasn't taken seriously until the early 20th century. Up to that point, most scientists, including Einstein himself, assumed the cosmos was static and eternal. Stars might be born and die. Galaxies might drift. But the fabric of space was considered fixed. The first cracks in that picture didn't come from bold theories at first, but from careful observations of light. In 1912, an astronomer named Vesto Slipher at Lowell Observatory started measuring the light from distant spiral nebulae, what we now know are galaxies. By breaking their light into a spectrum, he could see dark absorption lines where certain elements absorbed specific colors. Normally, these lines fall at very precise positions, like fingerprints of the elements that make up stars. But Slipher noticed something strange. In almost every case, the lines were shifted toward the red end of the spectrum. This was a big deal. Thanks to the Doppler effect, scientists already knew that light shifts depending on motion. Just like the pitch of a siren drops as an ambulance drives away from you, light stretches toward the red end when its source is moving away. Slipher's redshifts meant that most of these galaxies weren't just sitting still. They were retreating from us, and at astonishing speeds. At first, these results seemed puzzling and even controversial. Were these nebulae really separate island universes far outside the Milky Way? That debate was still raging, but Slipher's work had planted the seed. The universe didn't look static, it looked like it was in motion. A few years later, a Belgian priest and physicist named Georges Lemaitre took these ideas further. In 1927, working with Einstein's equations of general relativity, Lemaitre found a solution that didn't describe a fixed cosmos. Instead, it described a universe that must be either expanding or contracting. He proposed that the galaxies were flying apart, because space itself was stretching, and if you ran the clock backward, everything would converge to a primeval atom, what we'd now call the Big Bang. Einstein, upon hearing this, was dismissive. He reportedly told Lemaitre, "Your calculations are correct, but your physics is abominable." Einstein himself had bent his own equations to force a static universe, inserting what he called the cosmological constant to counteract gravity. Later, he would admit this was the greatest blunder of his career. While Lemaitre was working on theory, another astronomer, Edwin Hubble, was gathering the missing piece of evidence. Hubble measured the distances to galaxies using variable stars called Cepheids, which act as cosmic yardsticks. When he compared those distances with Slipher's redshift data, the pattern was unmistakable. The farther away a galaxy is, the faster it appears to be moving away. This relationship, now known as Hubble's law, showed that the universe isn't static at all. It's expanding. But what does it mean to say galaxies are moving away? Here's where the raisin bread analogy helps. Imagine a lump of dough studded with raisins. As it bakes and rises, the dough itself expands and all the raisins move apart. From the perspective of one raisin, it looks like every other raisin is receding, and the farther they are, the faster they go. Importantly, the raisins aren't flying through the dough. The dough itself is stretching. That's what space does with galaxies. There's no special center in the bread where the expansion begins. Every raisin sees the same thing. Likewise, there's no center of the universe where the Big Bang happened. It happened everywhere at once because space itself was created in that event. That's why asking, "Where did it start?" or "Where is it expanding into?" doesn't quite work. The balloon analogy adds another layer. If you draw dots on the surface of a balloon and inflate it, the dots all move away from one another as the surface expands. From the perspective of a dot, it looks like everything else is receding. But notice something subtle. The balloon's surface is two-dimensional, while the expansion happens into the third dimension of the air around it. People sometimes take this analogy too literally and think the universe must expand into some higher dimensional space. But cosmologists stress that the analogy is limited. Our universe doesn't need a third dimension of air to expand into. It expands within itself. Still, analogies only get you so far. The real proof came from the combination of redshifts and distance measurements. Hubble's data showed a straight line relationship. Double the distance, double the recession speed. This was exactly what Lemaitre's equations had predicted. Suddenly, the universe wasn't eternal and unchanging. It had a history, a beginning, and it was dynamic. And there's another strange consequence. If galaxies are receding because space is stretching, then light traveling across that space also stretches. Photons have their wavelengths elongated, shifting them toward the red. That means the further away a galaxy is, the redder its light appears when it reaches us. This cosmological redshift isn't about galaxies moving through space, but about the fabric of space itself stretching under their light. This is why, when we look deep into the cosmos, we see the universe not just as it is now, but as it was billions of years ago. The expansion of space stretches the travel time of light itself, letting us peer into the past. It also explains the cosmic microwave background, the faint glow from when the universe was just 380,000 years old, stretched over billions of years into microwave radiation that fills the sky today. By the 1930s, the evidence was undeniable. The universe was expanding. Lemaitre's once dismissed primeval atom idea started to look prophetic. But this raised a new set of questions. If the universe is expanding, where does that leave energy conservation? And perhaps most perplexing, if everything is flying apart, what happens to the universe in the far future? These weren't just questions of observation anymore. They required rethinking the very nature of space, time, and energy. And as we'll see, the answers don't always match our common sense. When we say the universe is expanding, it's easy to imagine galaxies racing through space like shrapnel from an explosion. That's usually the first picture people have in mind. A blast going off somewhere, hurling matter outward into empty nothingness. But that picture, while dramatic, is completely wrong. As stated earlier, the galaxies aren't flying through a pre-existing void. Instead, the distances between them are stretching because the fabric of space itself is growing. This is a subtle but crucial distinction. In everyday life, when something expands, a balloon inflating, a puddle spreading, a shockwave radiating outward, it expands into something. There's always an external medium, but in cosmology, expansion doesn't work that way. Space doesn't need an outside. It defines the inside. Expansion simply means that the scale of distances increases over time. Think of a map with a grid drawn on it. If the grid squares slowly get larger, then every landmark on the map appears to drift farther from every other landmark. That's expansion. The landmarks don't need to move across the paper. The paper itself stretches. In the real universe, the landmarks are galaxies, and the paper is space-time. This helps explain why no galaxy can claim to be at the center of the universe. From our perspective here in the Milky Way, it looks like every other galaxy is moving away from us. But if you were observing from the Andromeda Galaxy or a billion light years farther out, you'd see the same thing. Each observer sees expansion radiating away from their location, not because they're in a special spot, but because the expansion is uniform everywhere. For the balloon analogy, the only center of expansion exists outside the balloon, in the higher dimensional space it expands into. That's where the analogy breaks down, because our universe doesn't need that outside dimension. The expansion is self-contained. This is also why it's misleading to think of the Big Bang as an explosion in space. The Big Bang didn't happen at a single point that flung matter outward into emptiness. It happened everywhere at once. Every location in the universe today was once compressed into that early hot, dense state. The expansion of the universe isn't matter rushing outward from a point. It's space itself growing, carrying galaxies along with it. Another common misunderstanding is that galaxies are physically moving faster than light. When astronomers say very distant galaxies recede from us faster than the speed of light, that doesn't mean they're breaking Einstein's rules. Nothing can move through space faster than light, but space itself can expand at any rate. When the scale of the universe grows, the light travel distance between galaxies can increase faster than light could cover it. That's why there are parts of the universe we can never see. The expansion of space outruns light itself. Metric expansion is the technical term for this process. In Einstein's general relativity, the metric is the mathematical recipe that tells you how distances are measured in spacetime. When the metric changes, the scale of distance changes. It doesn't require matter to move anywhere. Instead, the ruler we use to measure the cosmos is stretching. That's what expansion really is, the changing geometry of spacetime itself, which redefines cosmic distances, making faraway galaxies appear to recede faster as the scale of the universe grows. This also explains why we don't notice expansion in our everyday lives. Atoms, solar systems, and even galaxies are bound tightly by forces that overpower the feeble stretching of space on small scales. Gravity keeps the Earth orbiting the Sun. The electromagnetic force holds molecules together. Local systems are stable. Expansion only dominates on the largest scales where gravity can't keep things bound. The vast gulfs between galaxies and clusters. That's why galaxies themselves don't expand, but clusters of galaxies drift apart over cosmic time. So, to put it in plain terms, the universe isn't expanding into anything. It's expanding within itself. There is no edge rushing outward into emptiness. The distances simply grow everywhere all at once. But this raises deeper puzzles. If distances are stretching, what happens to the energy of light traveling across those distances? Is energy still conserved in such a universe? And how does this stretching connect to the strange force we call dark energy that seems to drive it ever faster? Those questions take us beyond the simple picture of galaxies drifting apart. They bring us into the heart of modern cosmology, where even basic laws like energy conservation don't behave the way we expect. One of the strangest consequences of living in an expanding universe is what happens to light. When a galaxy billions of light years away emits photons, they begin their journey across the cosmos at a fixed wavelength. But as space stretches, those photons get stretched too. By the time they arrive at Earth, their wavelengths are longer, shifted toward the red end of the spectrum. This is called cosmological redshift. And it's not just a quirk of motion. It's built into the fabric of expansion itself. This is different from the Doppler effect that happens with sound waves. As in the earlier example of a siren moving away from you, the source of the siren is moving away from you, and so the pitch of the sound fades. In the case of cosmological redshift, of photons emitted from distant galaxies, it isn't caused by galaxies physically racing through space. Instead, it's caused by the space between us and those galaxies expanding, stretching the photon's wavelengths along with it. What's remarkable is how much information this gives us. By measuring how red the light has become, astronomers can tell how much the universe has expanded during the time the photon traveled. A galaxy with a modest redshift might be relatively close, while one with an extreme redshift, say its light stretched tenfold, must have been receding from us for nearly the entire age of the universe. This is why the most distant galaxies observed with the James Webb Space Telescope look so ancient. We're not just seeing faint smudges of light. We're seeing them as they were more than 13 billion years ago, because their light has been stretched across nearly the entire history of the cosmos. But redshift raises another question. If photons are stretched, they lose energy. Longer wavelengths carry less energy than shorter ones. So if the universe keeps stretching light, where does that lost energy go? Doesn't this break one of the most fundamental laws of physics, the conservation of energy? In everyday physics, conservation of energy is almost sacred. Drop an apple, and the potential energy it loses becomes kinetic energy. Burn fuel, and chemical energy turns into heat and motion. In a closed system, the total energy stays the same. But the universe isn't a simple closed box. It's dynamic, changing, expanding. And in this shifting geometry, energy conservation doesn't apply in the way we're used to. Einstein's equations of general relativity don't require global energy conservation across the entire universe. Instead, they conserve energy locally. That means in a small enough region of space-time, the rules hold just fine. But across cosmic distances, the stretching of space changes the game. When photons lose energy due to redshift, there isn't a neat place for that energy to go. It's simply a consequence of expansion. The law of conservation doesn't break. It just doesn't apply in the way we usually imagine. This feels deeply counterintuitive, and for good reason. Our whole experience of physics, is built on systems where the background doesn't change. Newton's laws, thermodynamics, even most of quantum mechanics, they all assume space and time are fixed arenas. But in an expanding universe, the arena itself evolves. The rules bend in subtle ways. Another strange effect of expansion is time dilation. Light from the most ancient galaxies doesn't just arrive stretched in wavelength. The events that produced it also appear stretched out in time. A supernova that would normally brighten and fade over a month might appear to take several months, if it happened billions of light years away. That's because the expansion of space stretches not only the light waves, but also the perceived flow of time in distant events. To us, the distant universe seems to evolve in slow motion. All of this has profound implications. It means the further out we look, the more distorted our view of reality becomes. We're peering into the past through a lens that literally stretches and dilates time itself. And yet, these distortions are exactly what allow us to reconstruct the history of the cosmos. The faint cosmic microwave background radiation, the afterglow of the Big Bang itself, is nothing more than ancient light stretched for about 13.8 billion years until it became microwaves. Without redshift, we wouldn't have access to that cosmic record. So, expansion doesn't just spread galaxies apart. It rewrites the way light travels, how energy behaves, and how we perceive time across the universe. It bends the rules we thought were unbreakable. But if expansion can stretch photons, alter energy, and distort time, what about the universe itself? Does it stretch forever, endlessly accelerating? Or could this process eventually reverse? The future of expansion, whether it ends in a freeze, a crunch, or something even stranger, is one of the most important questions in cosmology. And it all depends on a mysterious ingredient that scientists call dark energy. If there's one concept that completely reshaped our understanding of expansion in the past few decades, it's dark energy. Before the 1990s, most cosmologists assumed the universe's expansion must be slowing down. The reasoning seemed straightforward. Gravity pulls matter together. So even if the Big Bang set space itself expanding and carried galaxies along with it, the combined gravitational pull of all that matter should steadily decelerate the expansion. The big debate was whether gravity would eventually halt it, causing a collapse, the so-called Big Crunch, or whether it would simply slow but never quite stop, allowing the cosmos to expand forever at a diminishing pace. But then came a surprise that nobody predicted. In the late 1990s, two independent teams of astronomers led by Saul Perlmutter with the Supernova Cosmology Project and Brian Schmidt with the High Z Supernova Search Team studied distant supernovae, using them as standard candles to measure cosmic distances. These exploding stars are so bright that they can be seen across billions of light years. And because their intrinsic brightness is well understood, comparing their true brightness with how dim they appear allows astronomers to calculate how far away they are. The results were shocking. The supernovae appeared dimmer than expected, which meant they were farther away than they should have been in a decelerating universe. The only explanation was that the expansion of the universe wasn't slowing down at all, it was speeding up. Something was actively pushing galaxies apart faster and faster. That something was given the name dark energy. We call it dark not because it's literally dark, but because it's unknown. We can't see it. We don't know what it's made of, and yet it makes up about 70% of the total energy content of the universe. In other words, most of what drives the cosmos is something we don't understand. So, what is dark energy really? The widely accepted hypothesis in cosmology is that it's a property of space itself, a kind of vacuum energy. Even empty space isn't truly empty. Quantum physics tells us that particles constantly flicker in and out of existence. If space has a built-in energy, then as the universe expands and creates more space, there's more energy to drive expansion, making it accelerate. This picture fits nicely with Einstein's old cosmological constant, the fudge factor he introduced in his equations to keep the universe static. He later called it his biggest blunder, but ironically, it may turn out to be right after all. Other possibilities are more exotic. Some theories, such as those developed by Joshua Freeman, suggest dark energy is a new type of dynamic field, like quintessence, changing slowly over time. Others, like Robert Caldwell's phantom dark energy model, propose it might decay, disappear, or even reverse, causing expansion to slow again or collapse. These possibilities are hard to test, but they matter because the fate of the universe depends on them. To see why, think about the long-term consequences. If dark energy is truly constant, expansion will continue to accelerate forever. Galaxies, not gravitationally bound to each other, will drift farther and farther apart, until eventually, every galaxy outside our local group disappears beyond the cosmic horizon. Future astronomers, billions of years from now, would look out at the sky and see only their own galaxy. No evidence of a vast expanding cosmos, no hint of the Big Bang. The universe would become cold, empty, and dark in what's called the Big Freeze. But if dark energy is unstable, if it weakens or changes sign, the story could be very different. Some models predict that expansion could eventually stop and reverse, pulling everything back together in a big crunch. Others suggest an even stranger fate, the Big Rip. In that scenario, dark energy grows stronger over time, stretching space so violently that it eventually overcomes every other force. Galaxies get torn apart. Stars and planets disintegrate. Even atoms themselves are ripped apart as the very fabric of space-time unravels. We don't yet know which of these futures awaits us. But the fact that acceleration is happening right now is one of the most profound discoveries in modern science. It means the universe isn't just expanding. It's expanding in a way that defies intuition, driven by a mysterious energy we barely understand. What makes this even more puzzling is how finely balanced it all seems. In the early universe, matter and radiation dominated, slowing expansion. Only in the last few billion years has dark energy taken over and begun accelerating the cosmos. Why now? Why us? That question, sometimes called the cosmic coincidence problem, has no satisfying answer yet. Some scientists suggest it may be pure chance, while others wonder if there's a deeper principle at work that ties the timing of cosmic acceleration to the conditions for life itself. The mystery is that if dark energy had been stronger earlier, galaxies and stars might never have formed. Yet, if it were weaker, the universe might already be collapsing. Our very existence seems to hinge on this delicate balance, making the puzzle feel as much philosophical as scientific. For now, dark energy remains a placeholder label for our ignorance. It's the name we give to an observation we can't fully explain. But it's also a reminder of how strange expansion really is. The universe isn't just coasting outward from the Big Bang. It's being actively pushed. And that push comes from something deeper than matter or radiation, something built into space-time itself. And here's the key. Dark energy doesn't just change the speed of expansion. It changes the way we think about what expansion even means. If space itself has energy, then expansion is not just about galaxies drifting apart. It's about the very vacuum of the universe evolving. That brings us back to our core question. If the universe is expanding, is it expanding into something else? Or is it simply stretching itself, driven by this mysterious energy in the fabric of reality? To answer that, we have to dig even deeper into the very shape and structure of the universe. Because whether space is flat, curved, or infinite, changes everything about how we interpret expansion. By now, it's clear that expansion doesn't look like what our everyday intuition tells us. Galaxies aren't rushing into some empty space beyond the edge. Instead, the fabric of space itself is stretching, driven by dark energy. But that doesn't stop the question from resurfacing. What is the universe expanding into? It feels almost impossible to avoid imagining an outside, a surrounding environment, something beyond that we just can't reach. So, let's look carefully at the possible answers. The most direct answer from mainstream cosmology is nothing. The universe is everything there is, all of space and time. Asking what it expands into is like asking what's north of the North Pole. The question assumes a framework that doesn't exist. Expansion simply means the distances inside the universe are getting larger. No outside is required, and no border is being pushed. But there are other, more speculative possibilities that scientists take seriously, even if they're not proven. One is the idea of the multiverse, which comes from inflation theory. Inflation proposes that in the first split second after the Big Bang, the universe underwent a burst of super rapid expansion, much faster than anything we see today. According to some versions of inflation, our observable universe is just one bubble in a vast cosmic foam, with other bubble universes expanding in their own regions of space-time. In that picture, our universe could be expanding into a larger multiverse, though by definition, those other bubbles would be forever out of reach. Another angle comes from the mathematics of curved space. If the universe has positive curvature, it could be closed like the surface of a sphere. Travel far enough in one direction, and you might loop back to where you started. In that case, the universe would be finite but without edges, so there's still no outside required. Expansion would just mean the whole curved space is getting larger, like the surface of an inflating balloon. If the universe has negative curvature, it could be infinite, but saddle-shaped, endlessly stretching with no boundaries. And if it's perfectly flat, as current evidence suggests, it could also be infinite, with expansion, meaning that even infinity itself scales up, the distances inside it growing without limit. These different geometries are not just abstract ideas. They can be tested by looking at the cosmic microwave background, the faint afterglow of the Big Bang. Tiny patterns in that radiation reveal how space is curved on the largest scales. So far, the data suggests the universe is extremely close to flat, though we can't rule out a slight curve. That means the simplest answer is that the universe is either infinite or so large that its curvature is imperceptible within the part we can see. Either way, the expansion doesn't require an outside. Still, speculation doesn't stop there. In some theories, especially those inspired by string theory, our universe could be a brane, a four-dimensional surface floating in a higher dimensional space called the bulk. In that picture, the universe might literally be expanding into extra dimensions, dimensions we can't access. Gravity may even leak into those dimensions, which could explain why it's so much weaker than the other forces. If true, then expansion really does involve a larger environment beyond our universe, though one hidden from our direct observation. Another mind-bending possibility comes from the holographic principle. In this framework, everything inside our universe, space, time, matter, energy, could actually be encoded on a lower dimensional surface. If that's true, expansion might not be growth in the way we imagine at all. Instead, it could be the unfolding of information written on some distant cosmic boundary. What we call space expanding might just be a different way of describing changes in that underlying code. So, where does that leave us? The conservative, evidence-based answer is simple. The universe isn't expanding into anything. It expands by stretching itself. But the more speculative possibilities, multiverse bubbles, higher dimensional bulks, holographic boundaries, show that the question is far from meaningless. In trying to answer it, we're pushed to consider ideas that reach beyond ordinary space and time. And each of these possibilities has direct consequences for the future. Whether the universe expands forever, loops back on itself, or tears apart in a big rip, depends on the exact nature of space, dark energy, and whatever, if anything, lies beyond. If the universe is expanding now, then the natural question is, how does it end? Expansion doesn't just describe the past, it defines the future. Depending on what's really driving this growth, the fate of everything, galaxies, stars, even atoms, could be wildly different. For most of the 20th century, scientists debated between two simple options. Either the expansion would eventually slow down, stop, and reverse, leading to a collapse called the Big Crunch, or it would keep going forever, leaving the universe to thin out and grow cold in what's known as the Big Freeze. Both ideas made sense, depending on how much matter there was in the universe. Gravity pulls inward. If there was enough matter, gravity could eventually overpower expansion. If not, expansion would win. The discovery that the universe is not only expanding, but accelerating due to a mysterious force, now called dark energy, has reshaped our understanding of cosmic evolution. That changed everything. Suddenly, the Big Crunch looked unlikely, unless dark energy behaves in some way we don't expect. Instead, the Big Freeze became the leading scenario. In this future, galaxies drift farther and farther away until they slip beyond each other's reach. Stars burn out. Black holes slowly evaporate. After trillions of years, the universe becomes dark, cold, and empty. Expansion never stops, but nothing meaningful is left to expand. But acceleration also opened the door to another, even stranger ending, the Big Rip. If dark energy doesn't stay constant, but grows stronger over time, then expansion could eventually tear apart not just galaxies, but solar systems, planets, and even atoms themselves. Imagine a future where the pull of dark energy literally overpowers the fundamental forces holding matter together. Galaxies would disintegrate first, then stars, then planets, then molecules. Near the very end, even the protons inside atoms could be ripped apart. In this scenario, the universe ends not with a whimper, but with a violent unraveling of everything. There are also more exotic options. Some cosmologists wonder if dark energy could someday flip signs, turning into an attractive force. If that happened, expansion could suddenly reverse, leading to a big crunch after all. Others propose a big bounce, a cycle in which the universe expands, collapses, and then expands again, potentially repeating forever. In that view, the Big Bang wasn't the beginning, but just the latest rebound in an endless sequence. Each of these fates depends on what dark energy really is. Right now, the simplest model says it's a constant, something built into the fabric of space itself, known as the cosmological constant. If that's true, then the universe heads toward a big freeze. But if dark energy is more complicated, its changing strength could reshape the story completely. That's why astronomers are spending so much effort measuring distant galaxies, mapping cosmic structure, and probing the microwave background. all in hopes of narrowing down which future is in store for us here and now. Expansion doesn't affect daily life. Our galaxy is bound tightly enough by gravity that the stretching of space doesn't tear it apart. The same goes for our solar system and even atoms. Expansion is only noticeable on the largest scales. But in the far future, trillions of years from now, expansion is destiny. It decides whether there will still be stars, whether black holes will rule the cosmos, or whether matter itself will survive. And in a way, that loops back to the original question. What the universe is expanding into might not be the real puzzle. The real puzzle is what expansion does and where it ultimately takes us. Why does the question, "What is the universe expanding into?" feel so natural even though physics keeps telling us it doesn't need an answer? The truth is, it's not a flaw in the science. It's a flaw in us. Or rather, it's a reflection of how human brains are built to understand the world. We evolved to think on local, everyday scales. Our minds are tuned for throwing spears, planting crops, and navigating towns, not for reasoning about infinite curved spaces or the birth of time itself. When we hear the word expansion, we instinctively picture something with an edge, something growing into a larger environment. That's what we see every day. Bread dough rising into an oven, ink spreading in water, balloons swelling in the air. Our brains are hardwired to expect a container. Without one, the idea feels broken. That's why analogies like the balloon surface or raisin bread are so common in science communication. They help us get close to what expansion means without requiring us to abandon our everyday intuitions completely. But the price of those analogies is confusion. If the universe is like a balloon, people assume there must be an inside and outside. If it's like raisin bread, they assume there must be an oven around it. That's when the question, expanding into what, sneaks back in. The real challenge is that the universe doesn't behave like anything in our direct experience. Space itself can stretch, carrying galaxies with it without needing a container. This isn't just hard to picture. It's impossible to picture fully because our mental models are based on a world of objects, not space-time geometry. Physicists don't rely on pictures to understand expansion. They rely on mathematics, equations of general relativity, solutions that describe curved space-time and how it evolves. The math doesn't care about our gut feelings. It shows that expansion makes sense on its own terms, even if we can't visualize it. And here's where it gets interesting. That gap between intuition and reality isn't a weakness, it's a clue. Every time human intuition breaks down, it means we're brushing up against a deeper truth. Non-Euclidean geometry felt absurd in the 1800s. Quantum mechanics still feels absurd today. Yet, both turned out to describe reality more accurately than common sense ever could. The fact that expansion feels wrong might simply mean we're on the right track. This perspective also explains why asking, "What is the universe expanding into?" isn't a silly question, even if the technical answer is nothing. It forces us to confront the limits of our thinking. It pushes us to recognize that the universe isn't obliged to fit inside our mental boxes. In some sense, the question reveals more about us than it does about the cosmos. We crave borders, outsides, and edges. The universe calmly denies us all three. And that denial is part of what makes cosmology so powerful. We're not just learning about galaxies and dark energy. We're learning how to stretch our own imagination to match the scale of reality. The expansion of the universe isn't just a physical process. It's an intellectual challenge. It forces us to rethink what space even means, and to accept that our deepest instincts can fail when applied to the cosmos. So maybe the answer isn't that the universe is expanding into nothing. Maybe the better answer is that the universe is expanding beyond our imagination, and dragging that imagination along for the ride. Music. We started with a simple but unsettling question. If the universe is expanding, then what is it expanding into? On the surface, it feels like the kind of puzzle that must have a clear answer, like finding the missing piece of a jigsaw. But as we've seen, the deeper you dig, the more that question dissolves into something stranger. Expansion doesn't need an outside. It doesn't require borders, containers, or a surrounding void. Space itself is what grows, carrying galaxies with it, while time itself stretches forward. For most of history, humans pictured the cosmos as fixed, either eternal or static. The idea of an evolving universe was unthinkable. It wasn't until the 20th century with Einstein's equations, Hubble's telescope, and the discovery of cosmic expansion that we realized the universe has a story, a beginning, a middle, and potentially an end. That shift redefined not only astronomy, but philosophy itself. Suddenly, the cosmos wasn't just a stage for events. It was a character in its own right, changing and moving. The simplest scientific answer today is that the universe isn't expanding into anything at all. Expansion means that the distances between galaxies increase over time. No edge, no frontier, no beyond, just more space everywhere. And yet, the very act of asking the question has led to powerful insights. It's forced us to explore curved geometries, to wrestle with the nature of dark energy, and to speculate about higher dimensions, multiverse bubbles, and holographic boundaries. Even when the answer is nothing, the path to that answer opens entire landscapes of possibility. The future of expansion is still uncertain. Will the universe end in a slow freeze, a sudden rip, or a cyclical bounce? Will dark energy remain constant, or evolve into something else entirely? These aren't just technical details. They are the difference between a cosmos that becomes an empty graveyard and one that endlessly renews itself. The way the universe expands will ultimately decide what kind of story it tells. But beyond the equations and scenarios, there's something more human here. Expansion challenges us because it collides with our instincts. The universe withholds clear answers. Yet in doing so, it teaches us humility. It reminds us that reality is under no obligation to match our expectations. And perhaps that is the true gift of cosmology. It challenges us, stretches our imagination, and ultimately compels us to grow. So when you hear that the universe is expanding, don't picture a balloon in a room or galaxies rushing into a void. Instead, picture space itself stretching, carrying everything with it. Picture a reality that doesn't need an outside to make sense, and accept that sometimes the hardest part isn't finding the answer. It's letting go of the question.